In this video, we're going to talk about the finite limit of a function. So here's the definition. We say that the function f of x has a limit L at the point x equals a if the following holds true. If f of x can get arbitrarily close to L by choosing x sufficiently close to a. So really the limit of a function at some input value, a, is just what the output appears to approach as the input gets closer and closer to the input value a. We also have some notation specifically designed for limits. Our limit notation for the above statement that f of x has a limit L at the point x equals a is we write that the limit as x approaches a of f of x is equal to L. Alright, so now that we know the definition of a limit and we've got some limit notation, let's go ahead and do these problems. Compute the limits for the functions graphed below. First problem, the limit as x approaches 1 of f of x is equal to what? Well, let's take a look at the graph. What does the output value, the y value, approach as the input value, the x value, gets closer and closer to 1? Well, let's see. As x approaches 1, the function value is approaching this right here. And that point is 1, 3. So the limit is in fact 3. Now the function value is also 3, but the limit actually has nothing to do with the function value, as we'll see in the next example. Alright, onward to the next example. The limit as x approaches 1 of g of x equals what? So this one's a little trickier because there's a jump at 1, 3. At 1, 3, the function actually jumps to have the value 5, the point 1, 5, and then it goes back to how it was going normally. So what is the limit? Is it 3 or is it 5? What value is the function approaching as x gets closer and closer to 1? Well, let's see. As x gets closer and closer to 1, what happens to the function? It looks like it's approaching this point right over here, 1, 3. Now the function doesn't actually attain that point 1, 3, it jumps to 1, 5, but in limits we don't care what the function actually does at a point. We only care what the function attains near that particular x value, in the neighborhood of that x value. And as x gets closer and closer to 1, like say x is a half, the point would be right there, which is like 2.5. If x is like 0.99999, like nearly over to 1, then the function value would be just right below 3. So yeah, the function value is approaching 3, even though it doesn't actually attain that value of 3. So nevertheless, the limit is still 3. Alright, and how about the last example? Limit as x approaches 1 of h of x equals what? Well, this is pretty similar to the previous examples. We've got a point 1, 3, but now the function actually isn't defined at 1, 3 at all. Previously, we had the function defined at 1, 3, and then we had an example where 1, 3 was removed, but then the function was defined at 1, 5. But in this example here, the function value doesn't even exist for the x input of 1. But again, that's okay because with limits, we don't care what a function actually does at some point. All we care about is where the function looks like it's going. So we don't care that the function is not defined at x equals 1, we just want to know where does the function look like it's going based on the surroundings around x equals 1. And we can use that same kind of argument. Go to x equals a half, and you're like at 2.5, go to x equals 0.99999, so close to 1, and then you're like right below 3, you're so close to 3. If you go to x is like 1.00001, just barely after 1, then you're just barely above 3. So it looks like the function value is approaching 3 as x approaches 1, and that is the limit. So to recap, the big thing to remember here is that the limit of a function is not necessarily related to the function value. The limit might coincide with the function value, like in the first example, or it might be different from the function value, such as in the second example. Or maybe the function value doesn't even exist at a point, but the limit could still exist. And all of this is perfectly okay. Next problem. Which of the following statements are true concerning the graph of y equals f of x, which is shown below? First statement, the limit as x approaches -1 of f of x equals 1. Let's see, is that true? Let's look on the graph. Where is x equals -1? X is -1 right over here. And what is the limit value there? Is it 1? Well, 1 is that dot right there, and it looks like the function value f of -1 is 1. But does it look like the function is approaching that value based on the surroundings? Let's see. Well, based on the surroundings, as x approaches 1, the function is dipping down into negatives. And then same as x approaches 1 from the other side, from the right side. So the function actually isn't approaching its value of 1 here. That's just a little jump. And we don't care about jumps. We care about where the function looks like it's going based on its surroundings. Based on its surroundings, as x approaches -1, the function looks like it's going to this dot right over here. And the y value of that dot is -2. So the limit is actually -2. So 1 is not true. This limit is actually -2. Alright, so how about the next one? The limit as x approaches 2 of f of x is equal to 0. Alright, so let's locate where x is 2 on the graph. X is 2 right over here. And is the limit 0? Well, based on the surroundings, as x approaches 2, it looks like the function is crossing the x-axis. And indeed, that corresponds to a y value of 0. Now, the function isn't actually defined at the point x equals 2. There's just an open circle, no closed circles anywhere below or above it. But that's totally fine, because we don't care what the function actually does at 2. We only care what the function does around 2. And around 2, it looks like the function is just about to hit the x-axis, which means a y value of 0. So yeah, this is totally true. The limit as x approaches 2 of f of x is equal to 0. Alright, last one, number 3. The limit as x approaches -2 of f of x is equal to the limit as x approaches 1 of f of x. Let's just go ahead and evaluate these limits independently and then see if they're equal. Okay, so first of all, the limit as x approaches -2 of f of x. On the graph, x is -2 right about here, and let's go ahead and look up to where is the function approaching. So it's approaching all the way up here at the peak of this hump here, and that has a y value of 2. So yeah, the limit as x approaches -2 of f of x is equal to 2, and now let's go ahead and test the limit as x approaches 1 of f of x. So 1 over here, that's the x value for 1. And what is the y value that f is approaching? Well, the actual function value at x equals 1 is 0. But remember, we don't care about that. We only care about where the function looks like it's approaching. And this function value of 0 is a jump from where the function actually looks like it's going. The function actually looks like it's going up here to the top of this peak here, that open circle. And that has a y value of 2. So this limit, as x approaches 1 of f of x, is also 2. Okay, so the limits have the same value. They're both 2. 2 equals 2. So yeah, this is true. So now we know how to find the finite limit of a function, and in the future we'll gain a lot more practice with limits, including finding left and right-sided limits of a function.